In this lesson, we will continue our discussion of homomorphisms. In the previous lesson, we defined what a homomorphism is. It's a map from one group to another that preserves the group operations. One special type of homomorphism that we described is a bijective homomorphism called an isomorphism, which is used to show that two groups are essentially the same, which we called isomorphic. So let's begin this lesson by discussing how to show two groups are isomorphic. So if you believe that two groups are isomorphic, they're essentially the same up to just the labeling of their elements, then we need to define a isomorphism from one group to the other. So let G and H be your groups. First, we need to define a homomorphism from G to H. So define phi from G to H, and show that it is, first of all, a homomorphism. So we need to show that phi of xy equals phi of x times phi of y for all x and y in G. So we have a homomorphism, and then to show that it's an isomorphism, we need to show that phi is 1-to-1. Thirdly, we need to show that phi is onto. Then we can conclude that G is isomorphic to H. We need to define a function phi, show that it's a homomorphism, and that it's 1-to-1 and onto, and G must be isomorphic to H. Now the big theorem we proved in the last lesson can be used to show that two groups are not isomorphic, and we actually showed one example already of two groups that are not isomorphic. If two groups do not have the same structural properties, then they can't be isomorphic. So let's discuss how to show two groups are not isomorphic. We know that if two groups are isomorphic, then all their structural properties are the same. If we can show that one group has a structural property that the other group does not, then we can conclude that the two groups are not isomorphic. So let's find a structural property so for example, the order, the commutativity, so whether a group is abelian or not, etc. Find one of these structural properties that one group has but the other group doesn't have. So we showed that, for example, that Sn is not isomorphic to Sm when n does not equal m, since the groups have different orders. Now we'll give another example of this type of situation where one group has a structural property that the other group doesn't, and we can conclude that the two groups are not isomorphic. So let's consider the dihedral group D8. So this group consists of 8 elements that are the symmetries of a square. So they have 4 rotations and 4 reflections. So in this set, in D8, we have the reflection S, and the order of S is 2. So if you reflect across a diagonal and then reflect again across a diagonal, that will leave the original square unchanged. So the order of S is 2, since S squared is 1, the identity permutation. There's another element that has order 2 in D8. R squared would be the rotation of the square 180 degrees. So if you apply this rotation twice, that will leave the square unchanged. So the order of r squared is 2. Because if we apply r squared twice, so r squared composed with r squared, you get r to the 4th, which is the identity. So in D8, there are 2 elements with order 2. Now, in a homework exercise, we investigated the order of the elements of the quaternions. We actually showed that the elements of the quaternions, Q8, satisfy the following orders. Well, the identity has order 1. The element -1 has order 2, since -1 squared is 1. And then all of the other 6 elements of Q8 actually have order 4. So I, the order of I, equals the order of -I, which equals the order of j, which equals the order of -j, which equals the order of k, which equals the order of -k, and they all equal 4. So in a previous theorem, we showed that if x has order n, then phi of x has order n as well. So look at these 2 groups. D8 has 8 elements, but it has 2 elements with order 2. Q8 also has 8 elements, but it only has 1 element of order 2. So therefore, D8 cannot be isomorphic to Q8. So since the quaternions has only 1 element of order 2, we see that D8 cannot be isomorphic to Q8. So even though these are 2 non-abelian groups of order 8, we see that they're actually not isomorphic, because if we had an isomorphism phi of S would have order 2, and phi of r squared would have order 2 in the quaternions, which is impossible. It's actually a fact that D8 and Q8 are actually the only non-abelian groups of order 8 up to isomorphism. So any non-abelian group of order 8 must be isomorphic to either D8 or Q8. Now let's look at the group D8 a little bit more closely. So recall that D8 consists of symmetries of a square. So let's look at a square and label the vertices 1 through 4. So let's have a square. Let's label them 1, 2, 3, 4. Then each element of D8 is a symmetry of the square. It's some way to pick the square up and put it back down, and so that it takes up the same exact space. And then we can see all the different ways that the vertices can be permuted. And so in this way, we can actually identify each element of D8 as a permutation of the locations of the vertices. In other words, just a permutation of the numbers 1 through 4. So then each element of D8 can be identified as a permutation of the locations of the vertices. So each symmetry of the square just permutes the numbers 1 through 4. So for example, consider the permutation R. This is the permutation that rotates the square 90 degrees clockwise. So R, as a permutation of the numbers 1, 2, 3, and 4, would map 1 to 2, 2 to 3, 3 to 4, and 4 to 1. And cycle notation, we recognize this as the cycle 1, 2, 3, 4. And the permutation S reflects the square across the diagonal between the vertices 1 and 3. So it would take the vertices 1, 2, 3, 4, and it fixes 1 and 3, so 1 and 3 stay the same, but it flips vertices 4 and 2. So this would be the permutation S, and as a cycle, we see that 1 and 3 are fixed, and 2 and 4 are mapped to each other, so this is the 2 cycle 2, 4. If we think of D8 in this way as just permuting the numbers 1 through 4, we see that D8 is actually isomorphic to a subgroup of S4. So when represented this way, we see that D8 can be represented as a subgroup of S4. The permutations of the numbers 1 through 4. So again, recall that Sn, the symmetric group of degree n, is the group of permutations of the integers 1 through n. So D8 is a subgroup of S4, the symmetric group of degree 4, Now, if you have any set of elements, let's call it omega. So if omega is any set, okay, so not just the set of numbers 1 through n, then we can also define the group of permutations of omega and this group is called the symmetric group on omega. Denoted S sub omega. So the difference is when you're permuting the numbers 1 through n, we denote this Sn, but if you're permuting the elements of some set omega, we denote this as S sub omega. So if omega has n elements, then S omega is still isomorphic to Sn, but it's a little bit more of a general set. So we just showed that D8 is actually isomorphic to a subgroup of S4. Well, it turns out that every group is isomorphic to a subgroup of some symmetric group. And this fact is a very important theorem called Cayley's theorem. So this is the same Cayley that gave us Cayley tables. His theorem, he states that every group is isomorphic to a subgroup of some symmetric group. We already demonstrated this for D8. We showed that D8 is isomorphic to a subgroup of S4. Now, if G is a finite group with order n, then G is isomorphic to a subgroup of Sn. So every group is isomorphic to a subgroup of some symmetric group, and if G has order n, then it's isomorphic to a subgroup of Sn. So now let's give the proof of Cayley's theorem. So let's begin with any group G. So we must find a group of permutations let's call this group H, that is isomorphic to G. We're actually going to define an isomorphism between G and H. So we're going to use the elements of G to build this group of permutations. So suppose we have an element of G that's called X. So given an element X in G, let's define a function We're going to call this function p sub x to stand for a permutation that depends on x. So this permutation maps elements of G to elements of G by the equation p sub x of G equals x times G. So this function, whatever element of G you plug into this function, the output is x times G. So this is just a multiplication by x on the left function. So p sub x is just multiplication by x on the left. Then this function p sub x is actually a bijection. And p sub x is bijective. Let's prove this. Let's show first that p sub x is 1-to-1. So if p sub x of G equals p sub x of H, then x times G equals x times H, and by cancellation we can show that G equals H. So this shows that p sub x is 1-to-1. Now let's show that p sub x is onto. So given any element of G, we need to find another element of G that p sub x maps to G. Well, if we plug in x inverse G into p sub x, we get x times x inverse G, but by the associativity of G, this equals x times x inverse times G. X times x inverse is the identity, so we just get G. So we've shown that p sub x is onto. So p sub x is a bijection from G to G, so therefore it is a permutation of the elements of group G. So for any element x in G, we can define this permutation p sub x, and we're going to define our group H now that is isomorphic to G. So now let H be the set of all of these permutations p sub x. So it's a group of elements p sub x such that x is an element of G. So each one of these functions, each one of these permutations just is left multiplication by x. So we'll show that H is actually a subgroup of the symmetric group on G. We'll show that H is a subgroup of S sub G, the symmetric group on G. First of all, let's show that H is actually closed under function composition. Let's call this group axiom 0. P sub x composed with P sub y of any element G would equal P sub x of y times G, and that equals x times y times G. But this is the same as P sub x times y of G. So we see that H is closed under composition because P sub x composed with P sub y is just the permutation P sub x times y. So H is closed under function composition. Well, function composition is always associative, so axiom 1, we know that any function composition is associative. Next, we'll define the identity element of H. Well, 1 is the identity element of G, so P sub 1 of x equals 1 times x, which is just equal to x. So P sub 1 is the identity of H. And thirdly, we need to show that each permutation in H has an inverse. Well, given a permutation P sub x, if I compose it with P sub x inverse, so P sub x inverse composed with P sub x of G, this equals P sub x inverse of xg, which equals x inverse times x times g, which again we see when the x inverse and x cancel, we just get g. Therefore, the inverse of P sub x is the permutation P sub x inverse. Thus H satisfies all the group axioms, and H is actually a subgroup of S sub G. We started out with a group G. We produced a group H that's a subgroup of the symmetric group on G. And now we need to show that G is actually isomorphic to H. So let's begin by defining an isomorphism phi from G to H. So now we define the isomorphism phi from G to H by, given an element x and g, phi of x equals the permutation P sub x for all x and g. So we need to show that this is actually an isomorphism from G to H. First, let's show that phi is a homomorphism. So since phi of x times y equals the permutation p sub x times y, and we already saw that this equals the permutation p sub x composed with p sub y, we see that this equals phi of x composed with phi of y. So therefore, phi is a group homomorphism. Now we need to show that phi is bijective and therefore is an isomorphism. Well, by the way that H was constructed, we see that phi is onto. Because H consisted of all the permutations p sub x for every element of G, so phi of x must be onto. Now let's show that phi is 1 to 1. If phi of x equals phi of y, then the permutation p sub x equals the permutation p sub y, and that implies if we evaluate this function at 1, these functions at 1, we get p sub x of the identity 1 equals p sub y of the identity 1, which implies that x times 1 equals y times 1, so this implies that x equals y. Therefore, phi is 1 to 1. So we've just demonstrated that phi is an isomorphism from G to H, and therefore G is isomorphic to H, which is a subgroup of the symmetric group on G. Now further, if G is a finite group with order n, so if G is order n, then the symmetric group on G is isomorphic to the symmetric group of order n, and we see that G is isomorphic to a subgroup of Sn. And this concludes the proof of Cayley's theorem. So every group is isomorphic to a subgroup of some symmetric group. So we see that isomorphisms are very useful to show that two groups essentially have the same structure. There are certain kinds of isomorphisms that are referred to so often that they've been given special names. We look at one example of a special type of isomorphism from a group onto itself. This is called an automorphism. So an isomorphism from group G onto itself phi maps G onto G. This is called an automorphism of G. and the set of all automorphisms of G is denoted AUT of G. Now it is a fact that the set of automorphisms of G actually forms a group under function composition. So this set is often just called the group of automorphisms of G. So we've defined a special type of isomorphism from a group onto itself. We'll use isomorphisms and homomorphisms in general in the future, but we'll end this lesson with a couple of useful definitions. Given groups G and H, and suppose we have a homomorphism phi from G to H, we define the image of phi written phi of the group G. The image of phi is the set it's a set of all elements phi sub G such that G is an element of G. So for example, if phi is an isomorphism, it's by definition onto, so therefore the image of phi would be H. But in general, the image of phi is the set of all phi of G for any element G in G. Next we'll define the kernel of a homomorphism. The kernel of phi, denoted KER phi, is the set it's a set of all elements G in G such that phi of G equals the identity element of H. So phi maps elements of G to elements of H. The kernel of phi is the set of all elements of G which are mapped to the identity element of H. So this is the set of all elements in G which are mapped to the identity of H. Now with these two definitions of the image of phi and the kernel of phi, it can be shown that both of these sets are actually groups. In fact, the image of G is a subgroup of H, and the kernel of phi is actually a subgroup of G.